everyone, in the lecture today we will introduce the method to stabilize and improve soils so that we can gain better performance for pavement. Soil stabilization is the improvement of the soil so that it can perform a required function for the pavement. It could refer as the process of blending or mixing materials with the soil so that we can improve the certain properties of the soil. Usually it includes the blending of the soil to achieve the desired gradation, or mixing or commercialized available additive that may alter the gradation, texture, or plasticity, or act as the binder for cementation of the soil. Soil stabilization can also be the permanent physical and chemical alternation of soil and aggregates to enhance their engineering property, so that we can improve the loading-bearing capacity of the pavement. In general, the soil stabilization is proposed to improve the soil strength and reduce the compressibility. Also, we want to reduce the moisture susceptibility of some fine-grained soils with the stabilization process. We can also improve the property of the bore lines of the material so that it can be more stable on the road. Soil stabilization can also be applied for dust control, moisture control, salvage of the road, and construction of the superior bases. In soil stabilization, there are some basic principles we need to follow. First, we have to evaluate the properties of the given soil, including the strength, stiffness, and the impact of the moisture contents. And then, with the requirements of the pavement, we need to decide the laking properties of the soil to support the pavement structure. After that, we want to choose the most effective and economical method for the soil stabilization. The cost of the materials and labor work should also be put into consideration. Finally, we need to design the stabilized soil mix for intended stability and durability values. There are two types of soil stabilization. The first one is called a surface stabilization. In this type, the improvement of the soil only affects the zone with depth less than 1 meter. For most of the road pavement, the surface stabilization is applied. The second type is a subsurface stabilization, which is also called a ground improvement. It actually represents the geotechnical process of improving the engineering properties of the soil, and it can make the soil more stable and durable for the pavement and other construction work. In this process, the density, shear strength, cohesion, and friction angle of the soil are all improved, while the compressibility, settlement, and permeability will be reduced. There are many methods for soil stabilization. Generally, the selection of the method is determined by the economics, materials to be stabilized, the availability of stabilizing agents, and local experience. Basically, the methods of stabilization can be categorized into two types: mechanical and admixture stabilization. There are many methods applied for mechanical stabilization. The first one, which is also the most popular one, is compaction. We have already introduced the compaction procedure in the previous lectures. In general, this method is applied for unsaturated soil. It is able to increase the density, strength, and stiffness of the soil. The second method is adding more gravel to soils, especially silts and clay. The method will not have a significant impact about the strength and stiffness of the soil, and is also able to reduce dynamic stress level. The third method is blending, which is usually applied for soil with moderate plasticity. This method can improve the gradation of the soil and also reduce the plasticity and the breakage. However, sometimes in this method, it will be very difficult to mix the materials. The fourth method is called GEOSYNTHETIcs, which is usually applied for silts and clays. This method can actually increase the strength of the soil by minimizing the disturbance and consolidation. The method can be constructed at very high speed. However, Sometimes this method will cause long-term separation of the pavement. Finally, we will have the lightweighting filling method. It's usually applied for very weak seals, clay, and peat. This one is usually applied to prevent the frost heave effect. And the construction of this method is also very fast and is able to reduce the dynamic stress level too. Generally, in mechanical stabilization, there isn't any chemical reactions, and it won't change the composition of the materials. Instead, it will change the physical properties only, such as densification and reinforcement. Geosynthetics is one kind of effective reinforcement applied for the soil, including geotextiles, geogrease, and geomembranes. Here are some examples about geosynthetics applied in road pavement. We can see that there are some geotextiles or geogrease applied for the road pavement so that we are able to separate the soils at different layers. By introducing geosynthetic reinforcement, we are able to reduce the stress level in the subgrade. The two figures here shows the stress distribution at the subgrade layer before and after applying the geosynthetic reinforcement. For the figure on the left, we can see that the stress distribution on the subgrade layer is more concentrated, and that the value of the stress directed under the load is very large. While by introducing the geosynthetic reinforcement, we can see that the distribution of the stress is much flatter. In that sense, it has less chance for the load on the top of the pavement can cause the deformation to the subgrade, so that we were able to prevent the potential distress applied to the flexible pavement. Generally, the reinforcement functions of geosynthetics can be attributed into three mechanisms to improve soil properties for road pavement. The mechanisms include lateral restraint to shear flow, increased bearing capacity, and tension membrane effect to support road pavement. In general, the geosynthetic reinforcement is placed between the base and the subbase layers, or at the interface between the subbase and subgrade layers, or within the base course layers. The positions of the reinforcement in the pavement is very important. Usually we will observe higher bearing capacity when the reinforcement is placed at a lower depth. In pavement design, geosynthetics will usually perform four general functions. The first function is the separation of dissimilar materials. To gain this function, we will usually place geosynthetic reinforcement between subgrade and aggregate base in paved and unpaved roads and airfields. We can also place the reinforcement between subgrade and the balance of railroads, or between old and new asphalt layers. The second function is using geosynthetics as reinforcement of weak materials. In that sense, we have to place the reinforcement over soft soils for unpaved road, paved road, airfield, railroad construction platforms, and so on. Third, we can also use geosynthetics as filtration of the pavement. In that sense, we have to put the reinforcement under the aggregate base. Finally, geosynthetics can be used as one part of the drainage system. It could be applied as the drainage interceptor for the horizontal flow, or drain beneath other geosynthetic systems. The second type of destabilization method is admixture. This one will use some additives such as Portland cement, asphalt, to improve the properties of the soil for road pavement. There are some commonly applied stabilization agents. The first one is Portland cement, which is also very common in the road pavement. Portland cement can be applied for both coarse and plastic soils. The second type of agent is lime fly ash or lime fly ash. They are usually applied for plastic soil or the coarse soil with plastic fines. This kind of agent is able to improve the strength of the soil and reduce the moisture contents and the plasticity of them. They can also benefit long-term pozzolanic cementing. Usually for bituminous, it could be applied for coarse materials so that we can gain and improve the capability of waterproof for the soil. For plastic soil, we will need to introduce some chemicals so that we can improve the strength and volume stability. The cement stabilization might be the most common method applied for the mixture. There are a lot of advantages of using cement for stabilization. It's able to improve strength, compressibility, expansive characters, and reduce the susceptibility of soil. Usually we'll add 2 to 8% of cement by weight to the soil, and we cannot increase the percentage too much. With a very high cement, it will easily cause some cracks to the pavement. Also, the cement should not be used when there are some sulfate or organic materials observed in the soil. Also, usually when the cement is mixed with the soil, they should be compacted within 2 hours to a minimum density of 95% or as defined by H2O M134. And there are also a lot of factors affecting the performance of stabilization, such as the quality and quantity of cement, degree of mixture, time of curing, dry density of compacted materials, and so on. Usually for fine-grained soil with a higher plastic index, we need to increase the percentage of cement applied to the soil. For sand, it will totally depend on the volume ratio of the compacted materials. Bituminous stabilization is also widely applied for road pavement in reality. Usually, this method is applied for granular materials and is not quite suitable for fine-grained soil. In general, there are 2 processes in the method: hot process and cold process. In the hot process, the heated asphalt cement will be mixed with heated aggregate mixtures so that we can produce some high-quality hot mixture asphalt. In the cold process, we will mix the asphalt emulsion with soil, which will give us a low-quality material. Usually, this stabilization will have 2 advantages: waterproofing and cementation. With waterproofing, this method is able to reduce the water absorption of soil so that we can minimize the impact of the moisture contents. Also, this method is able to increase the cementation, which means we are able to increase the strength and cohesion of the soil. The stabilization can also be applied as the membrane to control the moisture in subgrade or subbase. Also, usually when we are trying to do the bituminous stabilization, we will mix them at a low moisture contents so that we can maintain a high quality of the material. The 2 figures here demonstrate the process of applying bituminous stabilization on the road. Lime can also be used for soil stabilization. Usually, lime stabilization is applied for fine-grained subgrade soil or crossways fines. In the lime stabilization, we will generally apply 1% lime by weight of every 10% of clay contents. But if we are working on some anti-erosion work, then we need to add more than 2% of lime for every 10% of clay contents. However, the selection about the amount of lime should be very careful. If we are working with clay of low plastic index, we should avoid too much percentage of lime so that we can avoid loss of cohesion. Also, the lime stabilization can increase the strength of the soil, but the strength gain is very slow with time. In addition, there are some benefits of introducing lime to the soil. By adding the lime to the soil, we are able to reduce the density of the soil and increase the soil strength and change the plastic index. In addition, if we put additional fly ash to lime, we can further increase the strength of the soil. Finally, for both cement stabilization and lime stabilization, they are all able to change the surface chemistry of the clay minerals. The soil stabilization can also be conducted with some chemicals such as calcium chloride and sodium chloride. With these chemicals, the soil can draw some water from the air and retain certain amount of moisture contents. With the appropriate moisture contents, we can keep down the dust on the surface of the road. Hence, the visibility on the road can be increased, and we are able to improve the driving safety of vehicles. Also, these chemicals can reduce the freezing point of water. In that sense, the impact of the freeze-thaw effect can be minimized. Usually, the chemical stabilization is applied for soils with clays. It has a lot of advantages, but the drawback of this method is also very obvious. This method can lead to corrosion of car tires and also cause some environmental problems such as contaminating drinking water. The figure here shows the guideline for the selection of admixture stabilization for each type of the soil. Basically, the selection is determined by the grain size and the plasticity index. In this figure, the black region represents the stabilization agent applied for each type of the soil. For example, if the soil has less than 25% passing number 200 sieve, then for any value of plasticity index, we can use cement, while only when the plasticity index is higher than 10, we can use lime. And if the plasticity index is less than 10, then we can use bitumen. While for the soil with more than 25% passing number 200 sieve, the cement is only appropriate when the plastic index is less than 10. And for lime, it could be applied for any soil with the plasticity index higher than 10. The flowchart here shows a more detailed guideline for the selection of the mixture stabilizer. First, we need to check the percentage of the soil passing the number 200 sieve. If the percentage is between 25 and 100, we'll go to the first group. And then we will check the plasticity index. If the plasticity index is less than 10, we will choose cement. If it's between 10 and 30, we will choose either cement or lime. If it's higher than 30, we can only take lime. And then if we find that the percentage passing number 200 sieve is between 35 and 100, and the plastic index is higher than 10, then we can use both cement and bituminous. If we find that the percentage passing number 200 sieve is less than 25, then we have to check three conditions. First, for the plastic index. If the plastic index of the soil is less than 6, and the plastic index of the part which will pass number 200 sieve is less than 60, then we will choose bituminous or cement. If the plastic index of the whole soil is less than 10, then we'll choose cement. If it's higher than 10, we will choose cement or lime. With that, we can identify the appropriate admixture stabilizer for all different types of the soils based on their grain size distribution and the plasticity index. That's all about lecture today in the soil improvement and stabilization. Thank you very much for your attention.